No intro, something might be alive under that ice right now. Let's go. Number 10. Subsurface ocean. You look at Europa and see ice, white, scarred, dead looking. But beneath that crust sits a global sea, and we've known about it for decades. The Galileo spacecraft caught it in the late 1990s. As Europa orbited Jupiter, it twisted the planet's magnetic field in a way that only made sense if a salty, electrically conductive layer was hiding under the shell. Not a frozen layer, a liquid one. How much water are we talking about? Roughly twice the volume of every ocean on Earth combined. All of it locked under ice, all of it in total darkness. So the question isn't whether Europa has water. That part is settled. The real questions are harder. How thick is the ice above it? Can anything from the ocean reach the surface? Can anything from the surface reach the ocean? Spacecraft images show long fractures and chaos terrain that behave like broken sea ice on Earth. Some regions look like they cracked open, shuffled around, and refroze. A dead, frozen world doesn't do that. If life exists on Europa, it almost certainly lives in that ocean, and that makes every discovery from here on a piece of the same puzzle. Number 9. Chemical ingredients for life. Finding water is one thing. Finding the chemistry that life actually runs on, that's the harder part. And Europa's got more of it than anyone expected. The James Webb Space Telescope spotted carbon dioxide concentrated in a young region called Terra Regio. Reanalysis of old Galileo data, using techniques that didn't exist during the original mission, turned up faint signs of ammonia near surface cracks. Ammonia acts like antifreeze. It drops the melting point of water and makes liquid pockets more likely inside the shell. On top of that, radiation from Jupiter constantly tears water molecules apart on the surface, producing hydrogen peroxide and molecular oxygen. Those oxidants could work as chemical fuel if they ever mix into the deep water below. And the part that matters most for the life question? Lab experiments show aromatic amino acids can survive for years if fresh ice buries them quickly enough. A few centimeters of cover is all it takes. Preserved biomarkers could be sitting just under the surface right now in the right spots, waiting for something to come scrape them up. Number 8. Water vapor plumes. In 2012, Hubble caught something odd, faint ultraviolet light near Europa's south pole. A team led by Lorenz Roth traced it to water vapor erupting roughly 100 miles above the surface. If Europa's venting ocean material into space, you don't need to drill through miles of ice to sample the sea. You fly through the spray and collect it. 4 years later, a separate group tried a different approach. They watched Europa pass in front of Jupiter and looked for silhouettes, plume shapes backlit by the planet's glow. On 3 out of 10 passes, they saw finger-like projections rising off the limb. Then in 2021, a review of 15 years of archival Hubble data found something else entirely. A persistent haze of water vapor clinging to Europa's trailing hemisphere. Not a single eruption. More like an atmosphere the moon keeps regenerating, probably through a different mechanism than the big plumes. The plumes themselves seem to be episodic. They may fire when tidal forces stretch the ice open at certain points in the orbit. If that holds up, it means the ocean can reach the surface on something close to a schedule, and a spacecraft flying through an active plume could sample ocean chemistry in real time. Number 7. Hydrothermal vents. Down on Europa's ocean floor, if hot rock meets salt water, the chemistry gets interesting fast. Those reactions produce hydrogen and minerals, and on Earth, that's enough to power entire ecosystems in permanent darkness. The best analog we have is the Lost City hydrothermal field in the mid-Atlantic. It runs on chemical reactions between seawater and rock, not volcanic heat. The microbes there don't need sunlight, don't need oxygen, and don't care that it's pitch black. They run on hydrogen and simple chemistry. If anything similar exists on Europa's seafloor, the conditions could work. Scientists have found traces of hydrogen and methane in Europa's environment, and carbon dioxide concentrated in young chaos terrain. That mix looks like what seafloor chemistry would produce, but some recent modeling suggests the seafloor could also be geologically quiet. Not enough tectonic energy to drive the kind of vigorous circulation we see at mid-ocean ridges on Earth. So we don't know yet. Vents might be widespread, or rare, or somewhere in between. What we do know is that the chemistry is testable. The right instruments flying through the right plume could detect the molecular ratios that would settle it. Number 6. Table salt on the surface. In 2019, Samantha Trumbo and Mike Brown at Caltech found sodium chloride on Europa's surface. Table salt, the same stuff in your kitchen, sitting on a moon 400 million miles away. For decades, everyone assumed the surface chemistry was dominated by magnesium sulfate, basically Epsom salt. Every infrared scan backed that up. The problem is that sodium chloride doesn't show up in infrared. It's invisible to those instruments. Trumbo's team figured out why. Jupiter's radiation constantly bombards Europa's surface, and when charged particles hit sodium chloride, the salt changes color. It picks up a distinct absorption feature in visible blue light. They matched it to lab samples irradiated under Europa-like conditions and found the strongest signal in Terra Regio, the same geologically young chaos terrain where Webb later spotted carbon dioxide. Why does this matter? Because if the ocean is rich in sodium chloride, it's chemically more like Earth's oceans than anyone had assumed. Not some exotic alien brine. Familiar salt water. And finding it in young terrain means it came up from below recently. The ocean and the surface are exchanging material. On Earth, sodium chloride forms when seawater circulates through hot rock. If that's what's happening on Europa, then energy, chemistry, and water are all converging in one place. Number 5. Tidal heating. Europa doesn't get energy from the sun, not in any meaningful way. What it gets is Jupiter. As the moon orbits, Jupiter's gravity stretches and compresses it like a stress ball. That flexing converts orbital energy into heat, and that heat is what keeps a global ocean liquid under kilometers of ice. Without tidal heating, Europa would be frozen solid all the way through. But the heat does more than just maintain liquid water. If it warms the seafloor enough, it could drive circulation, hot fluid moving through cracks in rock, pulling out hydrogen and minerals. One energy source, there's a second. Radiation from Jupiter cracks water molecules on the surface and produces oxidants, hydrogen peroxide, molecular oxygen. If those ever mix downward into the ocean, they'd work like a chemical battery. And a third, salt-heavy ice can grow dense enough to sink, carrying surface chemicals into the deep. Radioactive decay in Europa's rocky core adds a slow, steady trickle of heat and ions on top of all that. Any one of these pathways alone might be marginal, but 4 independent energy sources running in parallel. That's not marginal. That kind of redundancy is why Europa keeps rising to the top of every habitability shortlist. Number 4. Ice plate tectonics. In 2014, Simon Kattenhorn and Louise Proctor were studying Galileo spacecraft images when they noticed something unsettling. Sections of Europa's icy crust had vanished. Entire bands of surface terrain were simply gone along discrete boundaries. The only mechanism that fit was subduction, one slab of ice being shoved beneath another. Europa became the second body in the solar system after Earth where we found evidence of this kind of recycling geology, and it solved a problem that had nagged researchers for years. Europa's surface clearly shows spreading. The ice pulls apart. Fresh material fills the gap. But the moon isn't getting bigger. Where's the old crust going? Subduction answers that. It's being swallowed back into the shell. So why does this matter for the life question specifically? Radiation creates oxidants on the surface, compounds that could act as chemical fuel. If tectonic plates are diving back into the ice shell, they're dragging those oxidants with them toward the ocean. Surface fuel, ferried downward to wherever life might be waiting. A computer model published by Brown University in 2017 confirmed the physics checks out. Salt content variations between ice slabs create the density differences you need to make one slab sink under another, even without the kind of temperature-driven convection that powers tectonics on Earth. Europa isn't a frozen museum with the hidden ocean. It's an active system that churns and recycles. Recycling means mixing. Mixing means gradients, and gradients are what biology runs on. Number 3. Double ridges and shallow water. The most common surface feature on Europa is the double ridge. Two parallel raised lines flanking a central trough, running for hundreds of kilometers across the ice. They show up everywhere, and for decades nobody could explain how they form. Then in 2022, Riley Kohlberg's team at Stanford published a paper in Nature Communications that finally offered an answer. They found an identical structure in Greenland. Same gravity scale geometry, same proportions. And sitting directly underneath it, a shallow pocket of liquid water trapped inside the ice sheet. The mechanism turned out to be straightforward. The trapped water starts to refreeze. As it freezes, it expands, builds pressure, cracks the ice above it, and pushes material up on both sides of a central fracture. That's how you get twin ridges with a trough in the middle, and the same physics works on Europa. Consider the scale of that. Double ridges cover every sector of Europa's surface. Some are among the oldest features visible. If each one formed above a shallow water pocket, then liquid water isn't just locked away in the deep ocean. It's scattered through the ice shell, maybe within a few kilometers of the surface. The ice shell isn't a solid wall between us and the ocean. It's laced with liquid. Some of those pockets could host their own chemistry. Some might connect to the ocean below, and some could be reachable without drilling through the full shell thickness. Number 2. Juno's oxygen measurement. In September 2022, NASA's Juno spacecraft flew past Europa, and its particle detector, JADE, sampled the atmosphere directly for the first time. No remote sensing, no inferences from UV spectra. Actual in situ measurement. The results came out in March 2024 in Nature Astronomy, and they surprised almost everyone. Europa produces about 12 kilograms of oxygen per second, roughly 1,000 tons per day. That sounds substantial until you realize the models had predicted anywhere from a few kilograms to over 1,000 kilograms per second. Europa sits at the very low end of that range. Less oxygen reaching the surface means less oxidant available to trickle into the ocean. Every habitability model that assumed a generous supply of surface-derived fuel has to be recalculated. But less isn't zero. On Earth, some of the most ancient microbial lineages thrive in low-oxygen environments. They don't need much. They run on hydrogen and minimal chemical gradients, which is close to what a Europa seafloor environment might look like even with a modest oxidant supply. What Juno actually gave us is precision. Before this flyby, estimates spanned 3 orders of magnitude. Now there's a narrow band to work with. That kind of constraint doesn't kill the habitability case. It sharpens it. Instead of asking whether life is theoretically possible under some generous assumption, scientists can now model what kind of ecosystem is realistic given what Europa actually produces. Number 1. Europa Clipper. In October 2024, NASA launched a spacecraft purpose-built to investigate everything we've just talked about. Europa Clipper is currently on its way to Jupiter, carrying 9 instruments, and it's expected to begin close flybys in 2031. It won't orbit Europa directly. Jupiter's radiation belts would destroy the electronics too quickly. Instead, It'll orbit Jupiter and swing past Europa nearly 50 times, each pass targeting a different strip of terrain. Two instruments matter most for the life question. The mapping spectrometer, MIC, will chart organics, salts, and carbon dioxide across the youngest surfaces, the same kind of terrain where Trumbo found table salt and Webb found CO2. And the mass spectrometers, Maspex and Suda, will sample vapor and dust grains during close passes. If a plume erupts at the right moment, those instruments can taste ocean chemistry without ever touching the ground. So radar will probe the ice shelf for shallow liquid pockets, the kind the Double Ridge discovery predicted. A thermal imager will search for warm spots, and the magnetometer will nail down the ocean's depth and salinity with much better precision than Galileo managed. Clipper won't prove life exists. It can't. What it'll do is narrow the search from a global ocean to a handful of specific sites where the chemistry, the energy, and the access all line up. It'll point to where a future lander should dig a few inches into young ice and test for the chemical patterns that only biology produces. The first data arrives in 2031, and for the first time, the question of whether Europa hides life moves from theory to measurement.